Hi, I'd like to talk a little about coordinated motion. I've got here two motors connected to a Spike Prime hub, and it is relatively easy to make one of them move at a constant speed. It is relatively easy to start both at different speeds in an uncontrolled manner, so the speed is going to be governed, but the distance moved or the number of revolutions isn't. It is relatively easy to move one motor a certain number of degrees or a certain number of revolutions. But it is surprisingly hard to move both motors at the same time a given angle. And this is because in Spike Prime, in the word blocks, the movement blocks, the motor movement blocks, are, pardon the pun, blocking. What does it mean, blocking? It means that if I say, let the motor A run clockwise for one rotation, and I would like at the same time the motor B to move 2 revolutions, and if I start it, you will notice that it's the motor A that will move first and the motor B that will start moving only after the motor A stopped. It is because the block, the first block in this program, has to execute completely before the following block even starts. Now, this may be okay for many simple robots, but as soon as you've got some coordinated motion, or you need some sort of more advanced control over your driving base for first Lego League, this is going to be a handicap. This is going to be an issue that you will have to solve. Also, quite often it will be that you wish to move for 1, 2, 20 revolutions, but your motor may find an obstacle first. So you not only need to initiate the movement, but during this movement, during this motion, you need other commands, other decisions to be made, which will possibly break this. Because once the motor is running, you cannot really stop it. I mean, yeah, you can execute in a different thread the command stop motor. But once you execute it, all the control that you had over your motion is gone. You cannot say stop and go back a revolution from where you were right now. You just go for a full stop. Another issue that you've got here is when you want to do some coordinated motion. So like you would like to one revolution of the motor A at 75, say 50% speed, and then you would like to speed it up for the second revolution, for the other 2 revolutions to 75%, and you do it like this. You will notice that the motor stopped between here and here. It is not exactly always what you want. You might just want it that the motor sped up after 1 revolution. So, how to solve it? There are a lot of tutorials going around that show you sort of multi-condition loops where you start the motion in an uncontrolled way and then wait for a certain condition to happen in the loop, like wait for an angle of movement to reach a certain value, or you wait for the gyro sensor to report a certain value. And this is all a patch, because it means that you need to add more and more conditions into this loop, and this loop will execute slower and slower. And at the same time, you might want to do some position control during that time. So, no, this is not the way to go. The way this issue is solved in real world is by delegating the position control to a separate subroutine that is executed independently on the main program. And the simplest approach that generally works, it has its issues, looks like this. We've got 2 subroutines, each for one of our motors. We've got 2 motors, motor A and motor B. And everything they do is they just go in a loop, and in each loop they ask the motor to go to a relative position that is stored in a variable. And in the main program, we just change the value of this main variable. Why is it better? Now, if you think about it, when this block here executes, the change of the internal set point, the internal position that I want the motor A to go, does not stop the program execution. The change of the motor B position, target position, happens right after, immediately. And then the wait block comes. And in the background, the thread, the top rightmost, topmost thread, sends the command go to relative position to the motor A and waits for the motor A to reach this position. But this does not block the execution of the other part, which sends the same type of command to the motor B, which means both motors go in a motion controlled way to a new target position at the same time, not one after another. We can check how it works by just starting it, and you will see that both motors get different target positions. They start moving at the same time. They do not finish moving at the same time if you look very closely, because one has 90 degrees to go in each step, the other one has 120 degrees to go in each step. But each step starts at the same time, immediately, at the same time, the same moment. If we wanted to achieve that both motors also take same long, we would need to add a little bit of code here and change the speed for the motors, the desired speed, to be proportional to the distance they need to go. And this is a bit more complicated, but I would like to go in right here, and it wouldn't work very well anyway, because we still rely on the built-in blocks of go to position, which means the motor speeds up, goes at a certain speed, and slows down at the end. So even if we calculated perfectly the constant speed over the constant velocity period, we would still not have the motor stop at the very same moment, because the ramp up and ramp down times, they are coded into the block, into the hub. We don't we can set them independently. This approach has already this important advantage that you can generate new set points, new destinations for each of the motors independently and execute them, change them at the same time. It still has the drawback that once the motor starts moving, this block will keep executing, will block any further updates until it finishes. Which means that if in our main loop here, we by mistake calculated a large motion, and a split second later we would calculate a new, better position, the motor would still first go for the first destination before it would accept a new updated command for a new destination. So this means any sort of spike, any sort of fluctuation, any sort of mistake, any sort of bad large jump of target position will block the execution until this is executed, until the motor reaches the new target. And this means that at points we will have unwanted behavior, and we might want to update the target position before it has been reached. I mean, before the previous target position has been reached. So for example, for motion control of a robot, we would say what we think the destination for the next 5 seconds of motion are going to be, and then set the motors in motion, but after a second we will recalculate those values and update them, so to have fluid motion. And this here, again, it stops the motor after each target position is reached before accepting a new updated target position. So we need to improve the code. What can we do? We can build it like this. As you can see, I have here a very, very simple position controller. The main block looks exactly the same as it did before, but the subroutines that take care of the motors, they no longer tell them to go to a certain position. They adjust their power, or roughly they adjust their speed, and they do it in the dependence on the distance between where the motor should be and where it is right now. This is, in other words, a very simple linear controller. You can make a PID controller out of it. You can improve it in the way you want. A simple P controller is sufficient to demonstrate the principle. If I run the code, you will see that it works just as well. You could use possibly some fine-tuning. There is some overshoot, but the motors start and move in parallel. And this code does have this important advantage that those blocks are non-blocking, which means once they execute, once the motor power has been set, the block is over. So the loop executes again, executes again, executes again. So even before the motor reaches the target position can be changed. And indeed, I could replace this jumpy code by doing much smaller steps and reach some sort of coordinated motion. You will see that one motor, they move kind of jerky, but one motor moves exactly twice the speed as the other, and they are always keeping position in relation. So if you had some animatronic scene where one motor controls, the arm and the other one the head, then you could achieve this way that those two elements are kept in tune, in sync with each other. For such slow motion, better than just a P controller is necessary, but it's just the principle. And as you can see, the motors, they don't stop between the updates of the target position, even though they happen every 20 milliseconds. So this is already a much improved solution, but it still has one drawback, and you can possibly hear it. The motors keep whining, because although they have reached a good enough position, they are still powered at a very low power, but they are still powered. We never stop powering them. So the next improvement is a noticeable jump in complexity, but it actually solves two issues, one that I haven't talked about yet. Because sometimes we actually want the motion control block to be blocking, because we want to know when the motor reached its target position. It's not always that we just want to update it and don't care where it got to. But sometimes we simply want to wait until it finished the motion, because we have some action that's dependent on it. We cannot open the door until the latch has been lifted, or we cannot start the elevator before the door's closed. So there are situations where we want for the motion to complete. And this is the expanded code. And it actually includes a few updates. One is that the control code is not executed always, but it has a switch, a variable motor, in this case A and B. Those blocks are identical. I will go over only one of them. It has a switch which allows us to disable the motor control altogether. So if we set the control active to 0, this block stops executing, and we release the motor to whatever commands we execute in the main loop. Then we check if the difference between the position of the motor and the intended position is actually bigger than 5 degrees. 5 degrees is a tolerance band. Plus minus 5 degrees is what I accept as target position has been reached. And Lego motors, they generally do not have a better accuracy. If you want, you can try to reduce it to 3 degrees, and then you will have some erratic behavior maybe, but 5 degrees is a good rule of thumb value. It's a magic number, but it's experience number. It's the backlash of the gears in a Lego large motor. So if the target position is actually more than 5 degrees away from where the motor is, then we actually start to move. Only then. And what we do, we set another variable that we didn't have before. This is called motor A in position to 0, which means for the main loop, whatever other dependent control we want to implement, the motor is no longer in target position, and we start moving. And this is just the same P controller. Once the motor reaches the target position, then we set the in position to 1 and stop the motor. And if the control is disabled, then we also disable the brake. just so. I mean, I needed it that way. The initialization is a bit more complex in this case. We reset the position just for demonstration purpose. We reset the integrated relative position of both motors, set the set points to 0, enable the control, and everything else goes just as before. And you can see it will work. Now we no longer get the whine of the powered winding, because after the target position is reached, the motors are de-energized. I hope this is of help. If you've got any questions, just drop me a message, an email, a call. And right now, thank you for your attention.